Okay, here is a box problem that you will have on your test. Okay, we put this one on there because it's kind of an application of graphing these polynomials. Okay, we have a 16 by 20 inch piece of cardboard. So originally, all right, let's just say this was a 16 by 20 inch piece of cardboard. I cut x by x squares out of each corner. Okay, so I cut little squares out of each corner. And then if you would fold up the sides, you would be creating essentially an open-topped box. Okay? Use your imagination here with my great visual display. Okay? So I cut out corners. I cut out little squares in the corners and folded up the sides, and you create kind of this open-top box. But I could have a box that's this size. Or, if I cut out different size squares, I have a box that is this size. Okay? So they're definitely different sized open-top boxes, and it depends what size of square I cut out of each corner, right? Well, what we want to figure out is we only have a 16 by 20 inch piece of cardboard, but we want the box to be able to hold the maximum amount of stuff. Okay? So we want to make the best use out of the cardboard we have. Okay, well, which box is going to hold more? Well, you'd have to figure out the volume, wouldn't you? Okay? You have to take length times width times height. Now, you could sit here and guess and check all day long, or we could create a polynomial algebraic expression that we can solve to figure out where the maximum occurs. Because guessing and checking would take forever. Okay, so that's really what we're going to be doing here, is we're going to be figuring out how big of squares should we have cut out of each corner to make a box with the largest volume. Do you guys follow what we're going to do here? Questions on that? Okay, so originally, what was the size of cardboard we had?
16 by 20.
16 by 20, okay? So originally we had a 16 by 20 inch piece of cardboard, but we're going to cut x by x squares out of each corner and then fold up the sides. Okay? And then you'll have an open top box. This could be interesting.
Beautiful.
Okay? Then you'll have an open top box, okay? And we want this to have the maximum volume possible. Okay? Well, what are the dimensions of this box now? This was 20. So this was 20, but when we cut x out here and x out here, now it's only that long. So how long would that be? 20 minus 2x. Good job. Okay? This was 16, but again, we cut corners out, so now we're how much? 16 minus 2x. You guys with me on that? And then how tall would that box be? X. Yep. Because when you fold that much up, wouldn't that become our height?
Yeah.
So it's x. Questions on that? Do you guys see it? That's the important part, because it's too long of a problem to just memorize how to do it. Does that make sense?
Yeah.
Okay? So now, what's the volume of that box? How do you find volume of a box? Area, base times height. So we take this times this, right? Or length times width times height, if you prefer. So the volume of that box is going to be 20 minus 2x times 16 minus 2x times x. Now, I could multiply that out, but I'm not going to. Okay? You can still type this into your calculator. You don't need to multiply it out to type it in. Essentially, this still says y equals this. Okay? Could I graph this function on my graphing calculator? Yes. What power is x going to end up being raised to had I multiplied it out?
X squared. third.
To the third, right? When I have three x's being multiplied together. So what's the graph going to end up looking like? Probably something like this, right?
Yep.
Or something like that.
Mm-hmm.
Oh, you bet.
What's our goal? To find the, we want to find the box that has the what? Biggest or
Volume.
maximum volume.
Yeah.
So guess what do you think? What part of the graph do you think we're going to look at?
The
The local max. All you have to do now to solve this problem is graph this on your graphing calculator and see where that local maximum is. Okay? So you're just going to type this equation into your graphing calculator, just like we got done doing. Okay? And you're going to figure out where that local maximum is. You might really have to mess with the window now because this might be a large number. Okay? So let's type that into our graphing calculators. 20 minus 2x, 16 minus 2x, x. Need parentheses, just like we had it. So 20 minus 2x.
You're going to need to increase the window of the x and y.
16 minus 2x. And then just x. I hit graph, and oh shoot, I can't see, it looks like I can see a minimum, but do I really care about a minimum?
No.
In fact, would I even care about anything that's below the x-axis?
No.
That's not real. This is a story problem where volume is involved. Volume is never negative. So really, I just need to be able to see which direction. Higher, right? So when I go to my window then, the only value I really need to change is my what? Y maximum. That's the only one you really need to change. Let's change our Y maximum. I'm going to guess, I'm going to go to 1,000. I have no idea. I'm going to see if 1,000 is enough.
I guess 500.
500.
500 works?
Yeah.
All right, I'll take your guys' word for it. We'll just go 500. What's that?
200 was plenty for me.
Never. You have
Okay.
7 minutes.
All right. 200 was plenty? Your equation must not be right. Because that looks like, if I'm at 500 right now, I guarantee you this is higher than 200.
Yeah, 200.
200 was too low. Check your equation. Make sure you have 20 minus 2x, 16 minus 2x, and x.
Oh, I did 10.
Gotcha. Yep. Now all we got to do is find that maximum right there. Okay, how are we going to find a maximum? You guys tell me. Not trace, but
Calculate.
calculate. So second, trace.
Maximum.
Number 4, maximum.
And then
Left
find-
bound. I'm left of it right now, but I'm going to move a little bit closer. I'm going to have to move eventually anyway. So left bound. Right bound. Back to the middle. So you guys are seeing this maximum here. It's about 2.94, comma 420.11. Okay, there's my max. What does that mean then in terms of our story problem? What does the x represent? What does the y represent?
For Y represents volume.
Yep, this is the volume. This is the largest volume that box can have because look, all of these other coordinates right here are possible volumes. But are any of the volumes more than that one? No, that's the biggest one. Okay, that is the largest volume. So if this was this in inches, yes or no?
Yes.
So 420.1 inches cubed. There is my max volume. Okay, so the y value is my max volume. What's this x?
Wouldn't that be
That's
the
the-
square you cut
That's
out?
how big of a square you would have to cut out in order to get that maximum volume. So now you've figured out how big of squares you need to cut out of each corner of that cardboard to give a box with the largest volume possible.
So is the width 2.94 or is the volume 2.9? Or not the volume, the area.
the X, if I go back to that picture, it is the length. So this is 2.94 inches, this is 2.94 inches, that's 2.94, that's 2.94, okay? So that is the length of each side of the square you need to cut out of each corner. And if you do that, it'll give you that largest volume possible. So X equals 2.94, so really you're cutting 2.94 by 2.94 inch squares out of each corner. Okay? So on the test, I basically tell you, okay, you have a 16 by 20 inch piece of cardboard, you're going to cut squares out of each corner, figure out how big of squares to cut out of each corner, and then figure out what the maximum volume would be by cutting those amounts out. It won't be 16 by 20, it's going to be different numbers, but otherwise it's exactly that problem. Questions?